Hey guys, Kia from Kegland, and we're talking today about our BrewZilla Gen 4 and how to get the most out of it. And what I mean by that is some of our new accessories, such as the Bluetooth probe thermometer, which you can use to basically hit those target malt pipe temperatures which you're trying to achieve in the mash tun. Also, I'll talk about how to set up the PID temperature controller so you can easily do that yourself and optimize the heat up times without overshooting that temperature. And lastly, the other thing I'll talk about is this new heat exchanger dish, which is an add-on extra you can put into your BrewZilla Gen 4. We're thinking about possibly making it a standard, thing which comes with all the Gen 4s, but basically what this allows you to do is really hit those target temperatures faster and improve the heat exchange between the wort and the heating element in the base. Anyway, let's get stuck into it. So if you've brewed with the BrewZilla Gen 4 before, you'll know that all the Gen 4s and even the previous models came with this pump protection screen. The Gen 4 in particular had a dish shape to match the dish shape of the bottom of the boiler itself. And now we all have, bottom drain, which is bottom dead center in the middle of the boiler, which makes it really handy for draining all the wort out. But the accessory that we're talking about today is this additional accessory. So this is just like a stainless steel dish, and it follows a similar profile to the dish of the the false bottom screen here. So what happens is this dish sits in between the elements and also the pump protection screen itself. So I'll just put it on like this. You have to match up where the feet go into these holes, and then you've got a little wing nut here to secure it to the base of that protection screen. So I've screwed it on like that, and as you can see is a little tiny gap in the top here between the screens, about 7mm gap, and also there's an approximately 6 or 7mm gap between where the elements are and the screen itself. So what this does now, it basically will mean that the wort which is recirculating in the brewery will still pass through this screen and still get all the benefits of that pump protection screen, protecting hops and bits of malt essentially from getting blocked in the pump. But what we're doing is we're forcing the wort through a different path where it's forced to go right up against the elements. So let me show you in the CAD exactly what I mean. So the fastest way for me to probably explain this concept of what the heat exchanger dish does is probably in the CAD. So this is the CAD for the BrewZilla 65 litre, works the same with the 35 and the 100 litre. Anyway, I've got a cross-sectional diagram here where you can see the BrewZilla 65, and typically what you'd have is the wort running up this tube, so the wort circulation or the recirculation arm, then it would come over the top here, come through the hole in the lid, and then come into this malt pipe. So the wort would flow through the malt pipe. This would typically be like a perforated screen on the bottom of the malt pipe, but in this case it's just shown as a solid screen. And then we've got the pump protection screen, which is this screen here. And the pump protection screen obviously is there to protect the pump from getting blocked up with hops and grain and so forth. So, with this type of setup, it has worked fine, and pretty much all our other competitors manufacturing single vessel breweries have designed their breweries in a very similar way, I guess, where wort comes through the malt pipe like this, and it goes like that. And then typically, as you'd expect, the wort is going to take the path of least resistance. So as soon as it's gone through this sort of screen on the bottom of the malt pipe, it's basically going to take more or less a beeline to where the pump inlet is. So the pump drain is bottom dead center like that. So, some of the wort will be coming from the side here, and it would basically just go in like that. But quite a lot of it coming down the middle will essentially just come straight down the middle and then exit via the pump. So not a massive amount of contact with the elements necessarily. So sure, because the elements go the full width, I mean ours have very low watt density, pretty much everything in the base is going to be heated up. But really what we've found is we can greatly improve the heat exchange efficiency between the elements of the wort simply by adding this plate. So let me show you what this plate does. I'll get rid of that there like that. And then we'll go back to this CAD diagram, and the plate sits right here. So see highlighted in blue, it's basically a transparent dish. You can see here to make it easy to illustrate where it's sitting. It's sitting just below the pump protection screen and the elements itself. Now this is a solid screen, right? So the wort can't flow through this screen. So typically if I've got this screen in place, it looks exactly like this. So now what happens is the wort's forced down this sort of longer, more tortuous path. So as it exits, even if it exits down the middle of the malt pipe. Typically, if wort was to sort of fall through the middle of the malt pipe, it would go through the screen and then, typically just go straight down into this pump inlet, and that's it. Hardly any, contact with the heating elements. But, the beauty about this is it goes through the same plate, so it's still filtered, from the hops and malt and, stuff is filtered out of the process, goes out to the side of the plate, and then it's forced in very close contact with the element before it exits down the drain hole. So the nice thing about that is we're getting this large amount of contact time right against the elements. So this is what's giving us much more efficient heat exchange efficiency, and basically meaning we have got the wort pulling that heat out of the element and exiting down this hole. So if you're trying to do, step mashes and stuff like that, this will greatly improve the efficiency. So, even if it comes in from the outside, it goes down the same path and is forced up against these elements. So just so it's a little bit more obvious, I might change also the color here. So I've got the blue pen. So I'll highlight the elements with the blue pen here like that. And as you can see, the wort is coming in very close contact with these elements which are fused to the base. So that is why this will heat up so much faster. So that's how the heat exchanger dish works, but what we're trying to work out is whether we make it standard in all BrewZilla Gen 4s or not. Like, definitely other single vessel breweries that exist in the marketplace don't have them, but now we're thinking, it does definitely help the heat exchange. It means you can increase the temperature in your malt pipe faster, hit those target temperatures, and do those step mashes more efficiently. So for the small additional cost, maybe 10, 15 bucks or something like that, we're thinking about making this standard in all the BrewZilla Gen 4s instead of having to be an extra part you have to purchase separately. So if you guys feel strongly about it, definitely comment in the comments below, say hell yeah, would love to see the screen as standard, and if we get enough comments like that, we'll make it standard in all the BrewZilla Gen 4s we make in the future and just bump the price up slightly to suit. So that's enough for the heat exchanger dish. Let's talk about PID. PID is one of those terms in brewing you hear a lot, and you hear a lot of people kind of bragging about PID. Oh, my brewery's got PID, blah, blah, and all this kind of stuff. And often it's the case they don't even know how to set it up properly. And if you don't set up a PID, it's not really going to work that well. So that's something a lot of people don't kind of realize. And a lot of people think that if they have PID, they're going to hit that target temperature precisely and it's not going to overshoot at all and stuff like that. But if we were to make a really simple PID function which you just hit on or off and that's it, the reality is we would have to tone down the elements so much it would just come at a significant cost of power and heat up time in the first place, so you're not going to hit that target temperature for a while. Or the other problem would be it would just overshoot the temperature and hence not be very useful as a PID function. So you really need to be able to tune a PID, and you need to be able to get access to the controls somehow. So in the BrewZilla Gen 4 we've got the P, I and D coefficients which can be set up depending on what you're doing. Now if you change the volume that you're brewing, so for instance let's say you're doing a tiny 5 or 10 litre batch, or you're doing like a 20 or a 30 litre batch, your PID settings have got to be different. If you're using pump recirculation speeds that are different, that's also a thing. Like previously, the only control on the pump was this little valve on the side of the brewery here like that. But now we've got actually a pump percentage speed setting. So that's the recirculation speed which it goes through. So typically if you're at 20% or you're at 80%, that's going to require you to tweak the PID setting as well. And similarly, same with whether you insulate the brewery or not and stuff like that. So it is worth, if you really want to get out into PID and set it up properly, to learn how to tweak some of the settings. Right, so when you're first setting up the PID setting, the first thing you have to go into the settings and turn it on. So just hit the enter button here, then hit settings and go in here. Now, I will also mention that inside the settings, it has temperature hysteresis. Now, I've got it set to 0.0 because really we're not really focused on temperature hysteresis. So when you use the PID function, it really will kind of overwrite the settings in here and take over from any of the hysteresis settings. So just kind of, you can set them to 0 or completely just ignore them or whatever. And then go down to the bottom here where it says PID heating. So PID heating, I want to basically select this to turn that PID heating on. So now it's basically turned on. And with the P, I and D coefficients, Today we're going to basically set this up and tune in the P and the I coefficient only. That's probably all you guys need for brewing because we're dealing with a large thermal mass and it's not, building up and overshooting, too far or too fast. We're not really going to worry too much about the D coefficient, and a lot of industrial applications as often will only even use the P coefficient as well. So, you can make this as complicated or as simple as you want it. The D coefficient, however, there's a few exciting things down the track, which I think we might use that for distillation. Where that could be quite useful, but I won't talk about that in this video, and you guys can sort of research that one yourself if you really want to. But for the P coefficient, some of you guys may only set up the P coefficient and find that's perfectly fine. A good place to start with P coefficient is really in the 0.5 scale, which I've got it set here. So, when you're first starting to tune in the PID, just put it right in the middle of the scale there. And to give you some idea of what the P coefficient does, it's the proportional coefficient, which is what the P stands for. So it's probably best if I show you on a little bit of paper here. I was thinking about doing a digital graphic, but it was just easier for me to get out the old pen and paper. So let's say, I'm, trying to get up to 65 degrees Celsius and my ambient temperature is, I don't know, say 20 degrees Celsius like this, right? So I'm sitting down here. Now, if I've got let's say a very high P factor. So remembering the P factor basically goes between 0 and 1, right? So that's, the range of the P factor. So let's say if I've got a fairly high P factor, like P equals 0.8, for instance, what I'm going to notice is I'm going to approach this set point really quickly like this. So it's going to basically get up to the set point really fast, and only as I get really close, it's going to start scaling it down. So basically it'll go up really fast and then it will generally kind of overshoot a little bit like that if I've got a high P factor. So generally you'll keep tweaking up the P factor until you feel like you've got an acceptable level of overshoot. And if you think you're overshooting by too much, then just tweak that P factor down a little bit. So let's say I've got a P factor of 0.2, for instance. We're on the lower end of the scale. What it's going to do is it's going to crank the temperature up similarly at the beginning, but then it's going to start toning down that temperature earlier. So this will still have a tiny bit of overshoot like that, but it will be less. So I don't know if I've drawn that really well, but hopefully you can get the idea. Basically, with the lower P factor, it's going to start toning down the elements further away from the set point. Probably that's the best way I can describe it. Essentially what the P factor is looking at how far away you are from the set point. So looking at this distance here, or in the heating instance, it's probably this distance here when we're looking at most of the time. And basically the further we are away from the set point, it's going to basically increase the amount of power. So that's essentially what that proportional means. It's proportional to the amplitude of the wave that we're looking at. So let's go back to the controller here. Now look, I've already had a bit of a play around. So I've got this brewery filled up to the 30-litre mark and it's a BrewZilla 35, so I'm pretty much at full volume. Now, at full volume, I've found that a P factor and running the pump at 45%, I find that actually it works out to be pretty good round about, 0.68 or 0.7, somewhere in that range. So I'm just going to set this at 0.68. I find that at 0.68, it's significantly going to decrease the wattage of the elements as I get to round about, 1 or 1.5 degrees off the set point. And that usually means that I'm not really going to overshoot much at all. So that's how to set up the P factor. It's not that hard. Basically, keep increasing it until you're overshooting. And then if you feel like you're starting to overshoot too much, turn it back. So, I've got 0.68 there. And then you can go in and test that as well. So it's good to start with cold water and gradually keep increasing the temperature to see what the best settings are. So for instance, I've got the target temperature at 66. So I'm going to bump that up to, 68, for instance, like that. And then I'll just watch this temperature for a few minutes and see if I'm overshooting or not. So if I'm overshooting, just tone down the P setting. That's it. So with the I setting, that's another one you can go in and set up. So I'll go in here. So at the moment, I've got no I setting at all. You might find actually, if you're only using the P setting, sometimes actually you can get this situation where, I'll just draw this up on the pad here. So sometimes you find that if you're only using the P setting, because it's proportional, you can sort of start approaching that temperature, but it takes a very, very long time to get there as well. So, you know, the I setting can also be quite useful because, you know, it's one of those things that looks at the amount of time you've been off the set point. So let's say if we're using the I setting, it doesn't just look at how far we are away from the set point and scale that proportionally. It's an integral, so essentially it's kind of taking this area under the graph and then scaling that as well. So it looks at time, not just the distance, because obviously, you know, with the P setting, it's not really taking time into consideration. It's just taking how far away are we from the set point and then scaling the power. And then with the I setting, it's looking at how much is the total time spent, you know, off the set point, kind of in that way, I suppose, and I'm trying to simplify this as much as I possibly can. And then it's basically scaling it by that factor. So this is kind of handy as well in a PID setting. And look, typically, to give you guys a bit of a head start, if you've got a larger batch with more thermal mass, so you're operating at the full volume of the brewery, then you might find that a lower I setting is more useful. So for instance, let's say I've found with the I coefficient, oops, let's just go in, oops, not that one there. With the I coefficient, if I set it at 0.001 on a full batch, that works pretty well. So just want to set it at 10, then hit the enter button like that. It's going to save it at 0.00110. So yeah, that's how to set up the I setting. And yeah, if I find that, for instance, you know, if I've got a smaller thermal mass, so let's say I'm half filling this brewery, you know, the temperature is going to change more quickly in that instance. So I'm going to have to basically increase the I factor. So, you know, if you've got a half batch, round about 0.002 is a pretty good factor to start with. Anyway, here are a few of the settings that will get you started basically for a half batch and a full batch on the screen here. As you can see, the settings are quite sort of subtle in the difference, but if you try these out, they make quite a large difference. And I really can't emphasize that, even though it looks very kind of similar between the half batch and the full batch settings. If you use the full batch for the half batch, you'll be overshooting quite a bit, which really brings me back to the point that, you know, if you've got a brewery which suspiciously just has an on-off setting, I question whether it is actually useful or not. And it's probably more of a marketing gimmick for the brewery rather than actually being useful. So really, as much as we'd love to overly simplify PID, you do need at least some control of these different settings in the back end so that PID works really well. Now that's how to set up PID controller in a nutshell. But the question you've got to ask yourself now is, why would I necessarily want this amazing and high resolution control over the wort, which is down at the bottom of the boiler here? Remembering there's always going to be a temperature differential. So for instance, your malt pipe is going to be a certain temperature here, and obviously the probe inside the boiler down near the bottom, near the elements, is going to be picking up on the hottest temperature. So as much as setting up a PID is fantastic and it'll control that wort temperature here, is that necessarily what we're trying to achieve? And the question, and the answer to that question is no, not really, in my opinion, because when we're mashing in particular, what we're trying to achieve is a temperature inside the malt pipe. So, you know, when we're trying to get that mash conversion, this is kind of where the action is happening. Now, if you've purchased the BrewZilla Gen 4 and you look at the top screen, you'll probably notice that there's right in the top of the middle of the screen here, there's a slightly larger hole than all the other perforations. So these are like, you know, 1.5mm diameter perforated holes. And right in the middle, there's actually a 4mm hole there, or something like that, right in the middle. And the reason why we've done that is because when we first started making the BrewZilla Gen 4, we always knew we wanted to have the addition of a second probe. So a second probe like this gives you that extra level of control. Now this Bluetooth probe, instead of just using the temperature probe at the bottom of the boiler, which gets that hot temperature, and don't get me wrong, in all of these types of essentially rim systems that we're using, we need to have the probe near the element because we want to make sure we're not going to overly heat the wort either and kill all the enzymes, in that part of the brewery. So, it's still important, and if you've only got one temperature probe, really that's the place the temperature probe should be, is down near the elements. However, when we're mashing, what we ideally want to do is kind of like overly heat the wort in the base of the boiler in order for us to push the temperature a little bit higher. Now, not overheat too much, like overheat within a threshold, I guess, or a differential, but not so much that it's going to kill the enzymes, but going to push that temperature of the malt pipe up to the target temperature faster. And when we hit that target temperature, then tone it down. And that's exactly what this Bluetooth probe does. So this Bluetooth probe has a waterproof probe at the end, so you can immerse the entire thing. It's heat proof. We use braided stainless steel cable, and then that cable is then covered with a sheath of Teflon as well. So we go to quite a bit of effort to make a really nice and useful probe. A lot of temperature probes, which are often on a cable, don't seal the back of the probe in very well, and that's the reason why we've got it Teflon coated, is so you can dunk the whole probe in, and if you accidentally put it in too far or the water level goes even above this sort of joint on the cable, it doesn't matter. The whole thing is waterproof. So if you're using this type of device, you will have to pair this or bond this essentially with your BrewZilla controller to take into account both the temperature reading of this and also the temperature reading in the base of the boiler. Once you've got it bonded, then what you can do is get this temperature probe, put it down into the top of the screen, which is sitting in your malt pipe like that, and that's giving you a core reading of your malt pipe temperature. So let me show you how to set this one up on the display. Okay, so when you're setting up the Bluetooth probe, first thing is you need to turn it on. So just hold down the on button there until the screen illuminates like this. There we go. Now, if you leave it turned on, it's got an automatic turn off sort of setting as well. As soon as you turn that on, this will be giving out Bluetooth transmissions. So it's already sort of communicating every, I can't remember if it's every 10 seconds or so, but something in that vicinity, which the brewery can then pick up on. The other thing is it'll automatically turn off after about 2 or 3 days. So you'll notice that actually, after about 10 minutes, instead of reading the actual temperature on the probe, it just says BLE on the screen. And that means that the Bluetooth transmissions are still transmitting, but it's going into kind of like a power saving mode to make sure it's not always updating the screen. So that's why it goes into that BLE setting on the screen, but it still is functioning, perfectly fine when it does that. It's just power saving. So once I've turned that on, I go to the screen itself, and you need to go into the settings. So let's go down to settings here. And then first thing I need to do is enable the Bluetooth. So I'm going to go to that setting, hit enter, and that icon is now selected. Then I'm going to go back in the menu and then go down to Bluetooth. So I've actually already bonded the devices here. As you can see in the top of the menu, it says bonded and then unbonded devices. Now this office has these bloody sensors everywhere because they're doing a lot of testing. So there's basically quite a few in here, but you'll probably only see one unbonded device, and then click enter, and then it will appear as a bonded device up the top here. So now this one is already bonded, as you can see, and it's got transmissions. I can see that. See, it says last seen 2-3 seconds ago, and then it keeps repeating. So yeah, it looks like I'm getting a transmission every few seconds. Anyway, so once I've done that, I have to then return back to the settings because it's now receiving the Bluetooth transmission, but I'm not choosing this as the control temperature probe. So you have to actually select this as the control. So then I go into the settings here and then go into, where is it here? It says, I think it's at the top of the menu actually on my memory. There it was, yeah, so temperature sensor. So I click on that one, and yeah, I can select between the built-in probe and then the RAPT probe here. So this is obviously the RAPT Bluetooth probe, and it's got the last few digits of the MAC address there. So built-in probe obviously is that one in the base of the boiler next to the element. So yeah, basically I want to select this one like that. So now that one is selected as the control. And now when I go back to the home screen, you can see it's giving both temperatures. So I've got basically, the temperature on the Bluetooth probes. That's quite low at the moment because it's not even sitting inside the boiler. And then the built-in probe is 77.6. That's the elements are pretty hot in there. So as you can see, there's quite a big differential between these two. And the last thing I wanted you to show in the settings is a differential setting as well. So you'll notice, because we want to use the intelligence essentially of both of the probes, we don't want to necessarily only think about the Bluetooth probe and make all the decisions based on this. We want to make sure that that probe down at the base of the boiler is not getting too hot. So it should be within a certain threshold of the set temperature. So that's why we're also setting this other setting, which is called allowed sensor differential. So this 10 degrees means that if I've got the mash temperature set at 65 degrees, then it's going to allow the built-in probe, so the one down near the elements, to get up to 75 degrees before cycling them off. So, that's what's going to protect you from denaturing those enzymes in the bottom of the boiler. So I've found that actually 10 degrees works pretty well. Look, if you're really concerned about overheating your wort down near the elements, you set this to maybe 5 degrees or something like that. But look, I find 10's pretty good, so I'm just going to set it on the graph like that. And now that I've done that, this is really going to significantly improve my ability to hit those target malt pipe temperatures which I'm trying to achieve. So let me show you on a graph exactly what I mean. So this graph illustrates what you'd expect to see, in a typical setup without using the RAPT Bluetooth temperature probe. So if you're using the built-in probe, you'll notice that, let's say we've got a mash here and we're trying to build the temperature up from 60 degrees up to 65 degrees Celsius. So typically what will happen is, because it's got that probe right down at the bottom there and the amount of wort sitting underneath the malt pipe's quite small, you notice that small cavity of wort will heat up quite fast. Or go up like this, usually within a minute or a couple of minutes, it's already up by 5 degrees. And then you've got this set temperature at 65 degrees, and obviously depending on what your hysteresis settings are, it's going to bounce up and down, so 0.5 degrees above and below like that, and then basically just turn on and off and so forth. If you've got PID, it's probably going to be a little bit tighter than that. But anyway, the core malt pipe temperature, on the other hand, that's this green line here, that will go up quite fast to begin with. So as you'll notice, it's a big sort of thermal mass and takes a while for the hot wort, the 65-degree wort, to flow through the malt pipe. So you notice the temperature starts to climb up pretty quick, but as you get closer to the 65, the temperature increase starts to decrease. So what I mean by that is it gets harder and harder to get to that 65-degree core malt pipe temperature. So typically what you might see is it's increasing fast, and then maybe even after, say, 20 minutes, it starts to get very close, like it's 64.3 degrees, so it's almost getting to 65, but technically it'll never get there. It's actually just approaching an asymptote, because if you've got liquid, which is 65, the heat up temperature will never actually get to 65, but it's going to get close, and it's going to take quite a long time to get there. On the other hand, if you're using the RAPT digital temperature probe, you'll notice that the graph is going to look more like this. So as I was saying previously, we're setting that allowed sensor differential at 10 degrees. Now 10 degrees is pretty aggressive, admittedly. Some of you guys might go, oh look, I think that's too much, I only want to set this at 5. And look, that's up to you, you can set it to whatever you want. But look, I find 10 degrees is pretty fine. And what that means is that wort out down the bottom of the single vessel brewery heats up quite fast. So you'll see just like this, it heats up to the 65 degrees just as it would in the previous example. However, what it does is it keeps heating. Because our core malt pipe temperature hasn't increased, it goes, no, look, the core malt pipe temperature is still down here, so I'm going to kind of superheat that wort until that gets up to 10 degrees above the set point. So basically that's what I mean by that differential. So this setting here of that, that 10 degrees we're talking about, allowed sensor differential, is essentially this distance here between that temperature and that temperature. So setting at 65 goes up to 75 degrees, and then we'll bounce around within the sort of hysteresis figures around about the 75 degrees until we get our core malt pipe temperature up. So the core malt pipe temperature in this example increases very fast in comparison. So within sort of 5-6 minutes, we're hitting those targets much quicker. And as soon as that malt pipe temperature is reached, these elements down the bottom start to ease way back and say, hey, wait a second, we don't need to go so hot anymore, come back down to closer to the set point, and then similarly, it'll just bounce around that set point. So essentially what that means is we're hitting those, hitting the true malt pipe temperature instead of just trying to control the temperature down the bottom of the elements, that small amount of work down there. It also means we've got faster heat up times and essentially more accurate temperature control, because we're actually controlling the malt pipe temperature, not just the temperature right down near the bottom of the single vessel brewery. Well, thanks for that, guys. Hope you enjoy using the new RAPT Bluetooth temperature probe. I think it's an awesome product. It works with some of the other RAPT products as well. So we've got RAPT fermentation chambers and temperature control boxes, which you can also bond this device to as well. And I know it's been a long video, but I think it's important to cover things like how to set up PID and so forth, so you guys can work out whether you feel it's necessary or not to use those settings. But most of all, look, I hope you guys really enjoy using the BrewZilla brewery. It's one of these breweries out there now which is so feature packed that you've even got breweries which are double the price, which don't even have a lot of the features that we have, or have some very basic PID or Bluetooth add-ons like this. So due to a lot of the comments that we get, we've gone out and made a lot of the products that you guys have requested us to, and continue to do so. So, if you've got anything else you want us to get onto or make for you guys, definitely down in the comments below, go straight to our product development team and nothing gets missed. So, we'd love to hear from you guys. So comment below, and also sign up to our Facebook community group. So just jump on Facebook, Kegland Homebrew Community Group, and join that one and be part of the conversation there too. All right, that's it, and see you guys next time. Bye.